All right. Thank you, everyone, for sticking around still. And thank you for being in the live room instead of the suckers in the room viewing it over the screens. So my name's Colin O'Flynn, and I'm doing work on power analysis and clock glitching. So this is very much hardware attacks. And some of my objectives about this whole slide is to teach you about what is side-channel power analysis. So there is a little bit of theory, I'm sorry. But there's also quite a few demos of both the side-channel analysis and the clock glitching, as well as learning a bit about how to build your own hardware. So one of the questions I always sort of initially get or people wonder is, I have this fairly complete project that's both hardware and software, so is it commercial? So it's quasi-commercial. I've been working on this as part of a PhD, and there is versions of the hardware available to purchase. It's hard to make free open source hardware, but the best I can do is I do have a number of circuit boards here, so I'll put them up at the front somewhere. So if you want, come up and grab one of each, a red one and a black one, and there's instructions on how to build them and everything. All right. So there's quite a bit of documentation. This is all online now. There's an address there, and there'll be some other addresses later. So it goes through tutorials of how to use the tool, tutorials of running. There's a timing attack that's in the POC or GTFO that you have, and it shows you how to replicate that, basically step by step. Do this, do that, do that. And you can use, if you have something like a regular oscilloscope already, it's more than possible to use this. So you don't need to build very specific hardware. The software has built-in drivers for, in this case, it's like a picoscope device. So you can see there's the scope here. I have a target board. So basically when I'm doing these attacks, there's some sort of target that I'm attacking. So that's this microcontroller that's programmed. And then I also have a USB to UART there. So this goes to the computer. The oscilloscope goes to the computer. And then the software sort of orchestrates the attack. So unfortunately, what I'm not giving you out of this presentation is delicious sausage. This is what everyone wants. You want, side-channel analysis. It'll let me get the encryption keys. I don't need to know anything. I just run this script and it works. And it'll never work like that. All I can give you is plans for the sausage factory. And it's up to you to figure out, it's pork knuckle that goes in this or something. I don't know. And you've got to do it yourself. So because of how the attacks work, which I'll go over very briefly, it's very dependent on understanding the underlying theory behind them. So to sort of bring you into this slowly, we can begin with what is a side-channel attack in general. So when you say side-channel analysis, it's just something that's not, not the front door, it's through the window. As an example of this, there's a hard drive that's now end of life, but it has a little pin code on it, and if you put in the wrong pin, it doesn't enumerate properly. So it's pretty cheesy. But how they do the pin check, and you'll see this in lots of stuff, that you enter the 6 digits. After you enter the digits, it just has a while loop that's going through and comparing it. But you can see, and the theory is, there should be 1 million combinations of this password. So it's pretty secure. But the problem is, as soon as the while loop fails, it just exits. And you can see the amount of time it takes to do this comparison changing. So the correct password is 123456. If I enter 06666, we see there's this certain time delay. If I enter 16666, so the first digit is correct, it now takes a little bit longer to do that comparison. So you can actually just go through and you can have a script that or not a script, your finger is the script, and you have to check the button. Okay, now it's 1, the next digit's 2, etc. So in this case, it's worst case 60 tries to guess the pin. And it works quite well. So an extension of that is that previously I had an oscilloscope probe. So I had a probe on an LED that goes high when you've put in the wrong password, after you put in the password, and it says, no, that's wrong. So I use that. But lots of devices, will say, hey, I know that you can do this. I'm not going to be that dumb. So this is a very small bootloader for an AVR microcontroller. It's not a cryptographic bootloader at all. It's not designed to be that way. But it does have a very simple password check on it. And the password check, to avoid the timing attacks, as soon as you send a wrong character, it just stops doing anything at that point. It goes into an infinite loop, and you have to reset it. But it doesn't ACK characters normally, so you don't know when you've sent a wrong character. And this is measuring the power as I put in the correct password, and then it goes off and does something else. Now, if I put in the wrong password, you see something very different. So what's happened here is, I guess you can see, this byte, I think, is wrong, or one of these becomes the wrong byte. And as soon as it's received it, so at this point in time here, it's finished receiving that byte, and it says, oh, it's spin into an infinite loop. So you can see immediately where your password is wrong. So again, in this case, you do script it to try every combination for the first byte, or as soon as it sees, that this power level goes here, it knows the first byte's wrong, and then it keeps doing that until it gets the full password. So that's sort of what's generally called simple power analysis. So we're using the power of the device to learn just a little bit about what it's doing. But what's more powerful is what's normally called differential power analysis, or it might just be referred to as power analysis. But this is where we're actually breaking an encryption key of a embedded device or something like that. So this is where, unfortunately, there's a quick bit of theory for how this works. The overall objective is I have something that's doing a cryptographic function, like I'm using AES 128, but you can do it with other algorithms too. And you're able to send data to the device or watch the device as it's encrypting data. And you don't know the key, obviously, or anything like that. That's what you'd like to get. So it uses this pretty basic idea, and that's that if we have a digital device, inside the digital device, aka a chip, there's going to be different modules. The ALU might go to registers or something like that, and in between them, there's the data bus that the data goes across. Each of those lines of the data bus is basically a capacitor that, to set it high or low, you're driving it to 1 or 0. So it takes a physical electrons to do that, which means it takes power, which means that if you were to monitor the power on, say, the VCC line here, you could say, hey, at one instant in time, it took more power than at another instant in time, so it's probably setting more of those data lines high. So as an example, I have this 2-bit system here, and I'm saying, on this spike here, 2 of the data lines go high, and you see this sort of larger spike. Over here, none of the data lines go high. So from the VCC line, it's not taking any power because it's using it from the VSS or the ground line. So this is how we learn information about the what we call the Hamming weight, the number of bits on the data bus. And this isn't just some theory that it could work like this, maybe. So this is from a ATmega 328P, just a microcontroller, and I'm measuring the power as it's doing something with data of different Hamming weights, so different number of bits on the bottom. And you can see it's this quite linear relationship between 0 bits high, 1 bit high, etc. And something goes wrong up at 8. I don't know what happened there. Just ignore that part. So let's say you had that device, and it was doing something like this. It was just XORing some input with a secret key that's internal to the device. And you want to figure out what that secret key is. So we can send in a bunch of random data and the input here, and we can measure the power. So we're measuring the power across a resistor. The voltage drop across that will depend on the current, which we then use an oscilloscope to measure the waveform. So next what we'll do is we'll send in just a bunch of random data. So on the left side here, I'm showing you that I just sent it 88 and then XORed it with a secret key. And of course, I don't know the secret key. So really what it looks like is this. 88 and it did something with it. I sent hex 56 and it did something with it. But what we can observe is this Hamming weight value here. And this Hamming weight value, remember, is related to that intermediate value. So that's the information we have. And it's actually really simple how you figure this out. You can just do something like a guess and check. So this is all the very basic idea of it. And that's to say I could guess, well, what if the key was 0, 0? This is what I would expect the intermediate values to be if the key was 0, 0 when I sent it that data. If the intermediate value was 8, 8, I'd get some hypothetical Hamming weight leakage, which we're getting because we have this relation to the power consumption. Okay, well, it didn't look like that. Did it look like 1? No, it didn't look like that. Remember, we have this measurement here that we're trying to sort of recreate through guessing. And eventually you get to the point where you're guessing EF. So EF is the correct encryption key. And you say, hey, well, if it was EF, I would have expected 6-7 to be intermediate, which would have had a Hamming weight of 5, so my leakage would be 5. And this whole sequence now is actually agreeing with what the measured values were. So in real life, you can use something like correlation to correlate between the hypothetical value and the measured value. So this seems super dumb and simple still because it's just 8 bits, and I'm still doing a guess and check. So if you have AES 128, 128 bits, what was the big improvement there? And obviously this is that with AES 128, because it's doing the operation byte-wise initially, you can see that, for example, yes, there is 16 bytes, but for every byte, it does this operation where it XORs the key with the plaintext and then puts it through the S box. So if I look at the output of that S box, I can now do this operation, and I have to do it 16 times, but I only have to do 256 guesses 16 times. So it's trivial to do. I'm going to run it on my first generation Surface Pro here for you in a minute, so it's not a big deal. So what tools am I using? So the main tool is this, what I call the ChipWhisperer. So this is basically custom capture hardware. So it has an analog to digital converter on the front end here. It has an FPGA board, so this does the data recording and puts it over USB. The reason you may think, oh, well, it's just an oscilloscope. The main difference is it has hardware to allow you to synchronize to device clocks, which oscilloscopes won't let you do. And then it also has some other features. There's level translators, a USB programmer, and here it has the blinking lights, which are critical for any good electronics project. Actually, in the initial version of this, the lights didn't blink when you just plugged it on. You had to load the FPGA code. So in the new version, it does that when you plug it in. So that's like a big improvement. Anyway, so you can put it in a box. This is also, I don't have this version with me, but for travel, there's a box version. So that's the capture hardware. It just connects into a computer, whatever, laptop or something. And then I also have this blackboard. So this blackboard is simply what I call the victim board. For learning purposes, it just has a bunch of microcontrollers on it that you can program with code. There's an XMega, which has hardware AES and stuff like that. So it has some amplifiers built into it. If you were attacking a real system, you wouldn't have that board. You'd have your real system you're attacking. But in this case, because a lot of my work is about how do you learn how these attacks work, it's useful to have that type of platform. As I mentioned, as other tools, though, you can just use an oscilloscope. It works perfectly fine with that. And that's normally what people are doing. So if you have an oscilloscope already and are interested in this, you can build something like this. And again, all the plans for this board here, they're all up on the wiki and stuff like that. So I won't go through those details. There is lower cost versions, so if you don't have an oscilloscope and you want to build your own, so there's some lower cost FPGA boards you can get away with. This is an Avnet Spartan 6 LX9. So the FPGA inside my board is normally a Spartan 6 LX25, so it's a larger FPGA. You can basically cut some of the features out of the project and fit it inside a smaller FPGA if you want. And there's also the Papilio Pro, same Spartan 6 LX9 that you can use. And you can use some of these boards if you're just interested in glitching, for example. You can implement the glitch hardware in that, no problem. It's open hardware. There is software, so I'll show you this in more detail. So this is the GUI, for example. I have to warn you, though, I really am a hardware designer originally. So my software does stuff like right before this, I searched for, it's in Python, self.parent.parent.parent, and there's a few hits there. So there's stuff like this sprinkled throughout my code. So if you're really good at Python, feel free to contribute fixes. All right, so let's do a bit of a demo. Can you see? Yes. Okay, so the hardware that I have here is pull this over. It's just that red ChipWhisperer board. I don't know if you can sort of see there. And then there's that black board at the bottom. So it's exactly what was on my slides. And okay. If I run the ChipWhisperer capture software, there's basically a few scripts I have set up to do this attack right now. It takes a minute to, normally you'd go through and you'd be trying to find all the particular settings required. But I can run an example. So it downloads code to the FPGA, and then it'll send data to the AES core. So there's a Atmel microcontroller programmed with an open source AES library. And you can see this is the power it's using as it's doing AES encryptions. So for example, if I do stuff like if I set it to always send the same data, so fixed, you can see that the power signature, as I do one encryption at a time, isn't really changing. So you see tiny variances due to noise, but if I send different data, you can see that just how it looks is varying quite a bit. So it sort of shows you there is some dependence of the power on data. And one of the other questions, so right now, you need some way to synchronize approximately to where the encryption is happening. So right now I'm using an I/O line that goes high for determining the encryption is happening. In real life, of course, you can just say, well, I sent it the data at some point later. Between sending the data, getting the response, it's done the encryption. And there's a trigger, for example, you can trigger on an analog waveform in the pattern. So it's looking for a specific analog waveform in the power data. So this waveform can correspond to something like the loop that's initializing the encryption, the call to the encryption. It tends to be quite specific. So let me do this. So right now it's again doing the digital. Let me switch this. Digital encryption. So if I switch it to this pattern encryption, you should see the whole waveform slide over because now it's actually triggering on some pattern that I think is the load of the encryption data. Anyway, so it's very practical is the point. But what does it look like when you're really doing this attack? Set this back. So the first thing I would do is just record a bunch of data. So here it just sends 50 random plain texts to the core and asks it to encrypt them. And it saves the result as it's doing that. So it has 50 of these power traces and 50 of these the data, like the plain text data. And then it uses that guess and check algorithm to figure out what the encryption key is. So let me just call this test live 3. Just close that. And so in the analyzer, what you'll see is I'll open the data, and it'll print. So it's going to start guessing what it thinks the most likely keys is. And it does this as it adds in new data, basically one trace at a time. So ideally, you want to have a minimum number of attempts. So you want to send only a few attempts to the device under test. So this test live 3 is what I just recorded. And you can see that was the waveform. And approximately looks right. And on the attack, I'll just tell it to every 5 traces give me an update. And then on this table in red, it's going to have what the actual encryption key, which is like 2B7E something. And it only knows that because I've told it what the actual encryption key is because I set it in the device. So you can see there it's sort of filtering to the top already. And there it's completely recovered the encryption key from the embedded hardware device. So that's running regular AES that comes from an open source library. It's not some fake AES implementation. So the other question you often get right away is, well, that seems cheating because I'm strictly telling it to encrypt this and then measuring the power. But of course, in real life, this is basically what you get. So here's a AES 128 bootloader that's fairly well written. It comes from an Atmel app note because that way you get all the source and everything. But what you see, if you look into the block diagram, is basically you can send the bootloader a a frame, and it's going to try to decrypt it at some point. So it's going to check the CRC, which obviously you can do that easily enough. And then it's just going to decrypt it, and then decrypt it and verify the signature. And if not, it just gives you eventually it ignores it or something like that. But the point is, you can just send it garbage data, and you know the input data. You know when it's doing the decryption, so that's enough to get the key. In real life, there's some other steps to this, so you'd have to get the key first, get the initialization vector using more or less the same idea, and finally you have to figure out the signature, which if you look at the code, you can either do with a timing attack, or if you already had another upload file that was encrypted, you could just decrypt that now that you have the key and the IV. All right, so that's sort of half the project. The other half of this is dealing with glitching. So you already got a pretty good explanation of how glitching worked on Friday. So I'm not going to go at all over the background of it, because if you don't know, go watch that presentation again. So the clock glitching, it's basically the same idea as before. Again, we can insert glitches into a clock at some offset from the clock edge. My hardware in particular is always using this phase shift idea. So it has an input clock, which can come from the device or a generator or whatever you want. Creates two phase shift versions of it, and uses this to generate sort of a glitch stream, which it then adds some sort of trigger to and it. So you can insert a bunch of glitches if you want. Just as a side note to anyone doing FPGA stuff, so on the Spartan 6, there's this limited amount of phase shift you can do with the DCM blocks, Digital Clock Manager, I think it is, on the Spartan 6. So ultimately, what this project uses is partial reconfiguration. So it generates a bunch of like 512 different FPGA bit streams, and then generates different files from them and reprograms the FPGA on the fly. The downside of this is it takes like 8 hours to generate all these bit streams. So every time I change the project, I have to regenerate these bit streams. It's just a hassle, and that's why I tell people. All right, so as a demo, and I'll try to do this live, I have something like a password check. And if you have a point where you're doing some sort of comparison to, is the password okay? Ideally, we want to try to glitch that instruction so we fall through to the wrong side of the branch, or glitch one of the loops. So, and if it works, you would see, you put in the wrong password and you still get into the system. So the other thing we can do with this is voltage glitching, where we're dropping the voltage very sort of precisely on the system. So this is an example of like a voltage glitch waveform that I'm using. So it's normally running at 3.3 volts. And then on certain clock edges, you can see I'm trying to drop it down to close to 0 volts. So this can give you same sort of results as before. The voltage glitching can work when you don't have a stable oscillator. Again, I think that was all mentioned already. And to generate those, it's basically a very simple MOSFET system here. So it's this basically shorts your power pin of the chip to 0. So you can insert this into other systems pretty easily. When I'm doing these demos, I just have it right on the chip itself. So the one magic of this whole system is triggering, and that's inserting the glitches at the specific moment. So I mentioned one of the important ones, which is this sum of absolute difference. And so this is the analog pattern matching. So it's basically looking for some analog pattern by comparing it with the input data. And when that difference falls below some level, it triggers the system. You can also do stuff like, so the ChipWhisperer does support glitching on a digital data pattern. So this is a glitch being generated based on a UART byte going over the wire. When that UART byte goes over the wire, you can see it's then inserting 5 clock glitches in this case. So it is a very real threat to systems. So let's try the clock glitching demos. So these are a little more sketchy. Okay, so you can see everything. So to do the clock glitching, I'll first reprogram the AVR in 2 different ways. So the first one is just a loop. So it's pretty hokey. And again, this is to show you how how you can sort of start to look at this. So the first thing I'm going to use is this glitch1 function. And basically what you see is there's a variable, this a variable that gets set to 0. And then I just have this loop that says, well, a is not equal to 2, continue. So it should never escape from that. Before the loop, it prints a, and after the loop, it prints 1, 2, 3, 4. It also sets some I/O pins high and low so that if you have a scope, you can monitor it. So that's like a very simple loop, glitching out of a loop example. But we want to try to not glitch too far past the end of that loop. So I have a terminal emulator. So if I reset the AVR, just with this button here, what you'll see is it prints hello and then a. So I guess, yeah, can you see that? Ish. You can try this magnifier thing. Oh, crap. So there's the hello A. So it's stuck in the loop now. So what we're going to do is I'm going to go over to a glitch tab, and I can just close this. I can insert a glitch into the clock. And this is just a manual, I say glitch now, so there's no smarts about it. So there's this manual trigger button. When you hit this manual trigger button, it's inserting a glitch. So you can see the device just reset. It just printed hello and A again. And that's because I've probably inserted too many glitches at once. So if I insert, say, 3 glitches instead of 9, you can now see it's printed 2, 3, 4. So I've actually glitched a little bit past some of those instructions. So I can reset the AVR again and say insert just a single edge with a glitch. And then you can see this A, 1, 2, 3, 4, and then I hit it again and it resets. So you can glitch out of a loop that way. So finally, a little even more interesting example is let's load something with a password check. So I have this glitch3 file. And if you look at the source for this, basically what we have is it sends a request for the password. It reads in up to 16 characters. And it looks for the password of touch. And it does this compare. So this compare loop is designed to take constant time. And it sets a variable to say if the password's OK or not. And then if the password's OK or not OK, it prints welcome or not. So if I go back to my terminal emulator, you can see this password prompt. And again, once it's done, it'll reboot. So let me show you. So if I put in test, it says, nope, that's not the password. If I put in touch, I think I said, it says welcome. So it just reboots, every time. Oops. Welcome's not the password, touch. Right, okay, there we go. So now what I'm going to do is I can't do that manual glitch because I want the glitch to occur after I send the response back. So I'm going to use an external trigger. And so this is now set to trigger a glitch based on some event. And that event is entering that comparison loop. So if I say set a repeat of 5, it's not always working. So we'll hope for the best. So we're back at this password prompt. And if I put test, it says welcome. So it's actually glitched past the test of comparing the password. So if I put touch, it actually says F off, which should be the right password. So now it's giving me the wrong thing. But when I send the wrong password, it gives me the authentication prompt like it was OK. And I can turn this back off. So the interesting thing is that it's not even, we've glitched with fairly high precision past just a single point in time. And the glitch is now turned off, so if I send test again, it says nope, wrong. All right. In that case, the glitch trigger, for that demo, it's set up so that the microcontroller sets an I/O line high when it does it. You can do the same demo, and this is what I have here, is where the glitch trigger is based on the power signature itself. So you can see, for example, that some of these loops here, this is actually the while loop that's going over that 5 or 6 times going through the counter. So you can insert a glitch trigger on something like here, which is, I don't know, some initialization code, and then insert, this is the glitch occurring, this large power consumption dip. So in real life, you'd use something like that, but for reliability reasons, I have it set up to do an I/O line. So if you're interested, if you like this type of stuff, you can check out ChipWhisperer.com is the wiki. So there's some documents on that. You can grab, I'll have the PCBs up here if you want. There's bombs and everything online. And there's links to the Python documents, which includes all of the tutorials. Some of them you can just run on software, too. You don't even need hardware. So yeah, let me know if you have questions or how it works. And this is, again, what some of the tutorials look like. So this tutorial, for example, takes you through running a CPA attack purely with Python without even having any of the ChipWhisperer stuff. So that's it. Now it's coffee time, unless you have questions. No. How do you turn it? Okay, good.
So for the power analysis, how many samples was it usually taking till you'd have things at a consistent point where you could compare correct passwords to incorrect passwords?
So for the power analysis, it basically depends on the device itself. So for example, the AES, it takes about 3,000 points across, so like 3,000 samples within each trace. And then in that example for the AES, it takes about 20, I think, encryption. So I have to send 20 plain texts to it, and it encrypts that, which is fairly common for the AVR. If it's something like a hardware AES implementation, it might be a few thousand you need to send to it. A lot of the work done in this field, though, sort of has pointed to the fact that if you do better attacks, you can get away with, sometimes even sending a single trace to it. So you just send one encryption, and that's more than enough to break the password. So for the AVR, you can do that. The analysis takes longer to run, though, so you can't do it live.
All right, thanks.
Is it possible to do external triggering on SPI or serial?
Yep. So the digital trigger pattern in this implemented, it just looks for a. You basically just have to program it. This line goes high for 0 to 1 seconds or whatever. So as long as there's some digital pattern that you can predict, you can use that. Of course, you can just trigger in based on something else. So if you have another FPGA, you could program to, or you could implement in this, a SPI receiver, and just say, when the SPI receiver gets this byte, trigger. So that's sort of the idea of it. Other questions? Yeah, so the question was for more complicated protocols, what you would have to do, and absolutely, yeah. So the question is what's the most sophisticated chip you can work with? So this hardware, I think I forgot to mention, the sampling rate on this is about 100 megasamples per second, which is designed to run synchronous to the device clock. So you were talking, 100 megahertz. You can do some tricks where it's divided down and still maintains phase lock to the device clock. A lot of it is more related to sort of, for example, if it's a hardware AES implementation running at 200 megahertz, that's a lot more difficult than a software implementation running at 500 or 600 megahertz even. Because the software is taking so long to do each step, you can sort of get away with a lot of simpler hardware. There's demos where people are attacking software AES and they just are using a radio receiver to down convert to the to a lower frequency and then attacking on that. To what, sorry? So the question is if it's tied to the size of the FPGA. The FPGA on this board, you mean? So the limitation on this board is, it's a low-cost FPGA, so it can't run very fast, and the ADC itself has the speed limitation. So because it's designed to be fairly cheap, it's very limited in that way. I mean, you can buy fairly easily the SDR-type platforms are more or less doing the same thing for a few $1,000s, and use that instead. Okay. Cool. All right, thank you. So these will be up front.